Morning. Just gonna wait for a few more people to come in. Good morning. Morning, everybody. Okay, I guess we can get started now. Yesterday I intended to post some homework on the website, but I did not. Just to be honest, I forgot. I thought that I did, and then I checked this morning and I realized I hadn't. So I'm just going to post one homework sheet that just sort of covers the stuff that we did yesterday as well as today, and it'll kind of just be one homework set. Now this one might look a little bit different than some of the other homework sets that we've looked at in the past. It's going to be on the longer end, but I don't want you to do all of it. I don't want to overwhelm you with work. That's absolutely not my intention. So what I'm going to do is it's going to be quite a few pages long, it's from a textbook. But I'm just gonna tell you to do a few questions from each page. I'm not gonna get you to do the whole thing. So if you look at it initially and you feel super overwhelmed, don't think that you have to do the whole thing. I just want you to do a portion of it, because it's way too long. But it would just be really time consuming for me to make a new document that just has certain questions in it. So I'm just going to give you the whole thing, and I'll just tell you which questions I want you to do. And then also, if you wanted extra practice for some reason, then that would be available to you. At the very least, you'd be able to see what other questions might look like. Okay, so we're going to talk about something a little bit different today. It's not too outlandish, but it is a little bit different than what we've seen so far with radicals. It's called rationalizing the denominator. And I was doing this with my grade 11s yesterday as well. And I want to just tell you a little bit about how it works and why we do what we do. Because I think it's really important to try this, or not only to be able to do it, but to know why we do it. Because I don't think I was until well into university that I really understood why we do things like rationalizing the denominator. Because to be frank, it's a lot of work. It's not too bad, but you'll see that this process isn't a straightforward process, and it seems like we're not really doing anything. It seems like we're just taking one number and writing it in a different way. But you might also realize that that's kind of what we do when we simplify fractions. And simplifying fractions seems like it's kind of an important thing to be able to do, right? To be able to take a fraction that's like, something like this, like maybe 12 over 48, right? And being able to write that as 1/4. That seems like a reasonable thing to be able to do. And it's for almost exactly the same reason that we rationalize the denominator. It's and I'll talk about that in a little while. So yeah, let's get started. Let's start first of all by talking about what we're going to be doing here. So we are going to be rationalizing, which means that this is going to be a verb, right? This is a verb, so it's an action. We're going to be performing an action on something, and that something is the denominator. So there is our noun. Okay, so we're going to be doing a thing, or doing an action to a thing. So let's think about what that action is. I think that we all know what a denominator is, so I don't have to explain that to you. But rationalizing is a little bit, you might not know what that word is or what it means. So the idea of rationalizing a denominator is to take something that is irrational and turn it into something that is rational. So what I mean by that is, well, if I take a square root, so if I have a square root of a, and I'm going to assume at this point that a is an integer, okay? And in fact, this is true if I take any root, so an nth root, so that could be like a square root or a cube root or a 500th root, doesn't really matter. There's two possibilities when you take the square root or any kind of root of a whole number. You get two possibilities. One possibility is that you get an integer back. Okay, so for example, you could take the square root of 4, and that's going to give you 2. That's one possibility, that you just get a whole number back. The other possibility is that you get an irrational number. An irrational number. So for example, the square root of 2 is 1.41 something, and just like how you might already know that the number pi is like 3.14159 blah 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 blah. It's like it's a decimal number that has no pattern, no repetitions, and the decimals keep on going on forever. It does not terminate. That's your other option, is that you get an irrational number. So you get either a integer, which is like a nice whole number, something that we've been dealing with for many years, or the other option is that you get an irrational number. And the thing about an irrational number is that they're not very nice to work with, right? They're kind of nasty numbers. So when we rationalize a denominator, what that's talking about, so rationalizing, if I rationalize, it means to take a radical which is irrational and turn it into a rational number. Like, for example, an integer. Okay, so that's what we're going to be doing today. Is we're going to be looking at the denominator of certain rational expressions, so like one term above another, and the denominator is going to be an irrational number, so you'll have something like the square root of 2, and we're going to try to change that expression so that the denominator is no longer an irrational number. We want a rational number on the bottom. So let's take a look at what that might look like, and I'll do one example and then I'll tell you why we do this. Okay, I'll do one example and then I'll tell you why we do this. So actually, I think I can go over here. Yeah, Why don't I go right beside my old work? Okay, so let's take a look at what we might have to do. So I could have an example that looks like this. So we'll rationalize the denominator. Okay, and I'm gonna have something that looks like this. So I'll have 5 over the square root of 2. Okay. So wouldn't it be nice if we could just like say that this is equal to 5 over 2? Like that would be so nice. But the thing is, these are not equal. This is not equal to 5 over 2. You can't just remove the square root symbol because they're not equal. We want to find, like our goal is to find an expression that is equal to 5 over root 2 that has a denominator that is rational. Right now, the denominator, so the square root of 2, is irrational. If you don't believe me, take a look. So I'll do it right now. So the square root of 2 is 1.4142135623 blah 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 blah, and I'm sure that Wolfram Alpha is going to tell me that it's irrational. Oh, and look, it even has a constant. It's called the Pythagoras' constant. So there's the real principal root. I guess it doesn't tell us here that it is irrational, but I think that you can see, look at all these digits. There's no pattern here. It keeps going and going and going and going, right? So so the square root of 2 has many digits. So and there's no pattern. It's just like pi, how there's no pattern. It just and there's no repetition or anything like that. It just keeps going on and on and on and on and on. So we don't want that in the denominator. And I'll tell you why in a minute. Like I'm kind of saving that. So here's what we're gonna do. So I'm gonna say that these two things are equal. So 5 root 2 is obviously equal to 5 root 2. Now the trick, the way you do this, is to multiply the numerator and the denominator by root 2. Root 2 over root 2. And I think a couple days ago there was a question that was very similar to this on the homework. I forget exactly which question, but there was a question that had said something about not having any fractional exponents in the denominator. That's the same thing here. It's exactly the same thing. So anyway, the way we would deal with this is that we would get 5 over root 2 over, well, root 2 times root 2 is just equal to 2. And now, look at that. Our denominator of 2 is rational. So 2 is rational. Okay, so just to be clear, and I think that we've done this a few times, let's be clear about what rational means. Let's be clear about what rational means. Okay, so we have our different number systems, right? We have our counting numbers. So that's numbers like 1, 2, 3, and so on. Then we have our integers, which are these ones. And these ones have like -2, -1, 0, 1, 2, etc. So there's no beginning and no end, but it's still just whole numbers. It's like, you know, I mean, there's negatives and positives, but there's no decimals or anything like that. After that, we have the rational numbers. Okay, so these are all the numbers that can be written as a fraction, where A and B are integers. Okay, and then after that, we have the real numbers, which is everything else. So it includes things that are irrational. Okay, so these irrational numbers, these are in here. So the square root of 2 is in the set of real numbers. The square root of 2 is not in the rational numbers. Okay. However, this guy here, 2, 2 is a real number. So 2 is in the set of real numbers, but also 2 is in Q. So it is in the rational numbers. So 2 is a rational number. So we're good. Now, let's talk a little bit about why we do this. Like, why on earth do we do this? Because it seems like it takes a lot of work, right? Like, it's not a straightforward process. And we'll see in a minute that some of these questions, they're pretty hard to do. It actually takes a substantial amount of effort to rationalize the denominator. So why do we go through all the trouble to do that? Well, let me tell you. So why? So here's my motivation. So why, here, I'll make this nice and big. Why do we rationalize denominators? Why do we rationalize denominators? Well, there's as far as I can tell, there's one good reason. Nice. Goose really wants to take part in this. Yeah. Okay. Hi, sweetie. Glad you're here. She wants to lie right on my iPad. Thanks, dear. I don't know if you can see her. She's lying right where I'm supposed to be working. It's almost as if she knows. Okay. So why do we rationalize denominators? What's the point of this? Because, like, if you really look at what we did over here, we didn't really do anything, right? We just changed. Goose, that was her moving the iPad. Oh, you're so cute though. Oh my gosh, how can I possibly ever do any work when there's such a cute little cat right under my chin? I'm getting very distracted here by my sweet, sweet little cat. Why do we do this? It doesn't look like we did anything. We just changed one number. We changed this number over here to this number over here. And it's the same value. We just changed the form of the equation. So, like, why go through all the trouble, right? Like, what is the point? And it wasn't until I started taking some algebra classes, and this is my book. It was a contemporary abstract algebra. It wasn't until I was in my 4th year of university, when I was studying fairly challenging topics in abstract algebra, that it finally dawned on me why we actually do things like rationalize the denominator. And it actually makes a lot of sense when you sort of think of it this way. Okay, sweetie, you gotta move. Oh, love her so much. Okay, so why do we rationalize denominators? Well, the main reason, as far as I can tell, and this is kind of coming from like an algebra background, is well, let's consider this. So any value has an infinite number of expressions that represent it. Oh, Goose. That represent it. I don't know if you can see Goose here, but she's being very distracting. She wants attention. Okay, so any value has an infinite number of expressions that represent it. So if you don't really see what I'm talking about, take like any number. Let's take the number 1/2. Well, how many different expressions can we think of that represent 1/2? Well, how about 0.5? How about 4/8? How about the square root of 2 over 2 times the square root of 2? Right? Like, there's an infinite number of expressions that represent it. Like, we could even have like 5 plus 7 over 48 8 divided by 2. And I'll, no, that's right. So yeah, you can check for yourself. I think it's 12 over 24, which is 1/2, right? So there's many ways that you can write 1/2. There's an infinite number of ways. So at some point we have to say, okay, look, what is the one representative way that we can express this value? So mathematicians often ask themselves, so how do we represent this value? Like, is there like a representative in all of these expressions that's like, okay, all of you guys are equal to 1/2, but like I am like the real version of 1/2, and oh my goodness, you're just adorable. I'm sorry if you're getting annoyed by my cat, but she's like, I can't help myself. She's just being just too much. Too much. Okay. So at some point we have to say, okay, well, like which one is the real half? Like would the real Slim Shady please stand up? Like that kind of thing. So with fractions, we say that the reduced fraction is the representative. Okay, so in this case, the representative of 1/2 is this guy right here. It's 1/2. That's like the main representative of that value, right? There's an infinite number of ways of choosing how to write it. The one way that mathematicians and humans in general have decided that we actually think like the pure version of 1/2 is 1/2, right? All of these other guys, they're the same. They mean the same thing. But 1/2 is like the representative. It's like the poster boy for the value of 1/2 is 1/2, right? So it's for that reason that we rationalize the denominator. So when we rationalize denominators, so when we rationalize a denominator, we are finding its representative value. Okay, so we're not changing the value itself, we're changing the form of the value. So we're finding an equivalent expression that has the same value, but we've decided as mathematicians and humans and just as a society in a way, that the way we represent these values is that we don't want to have an irrational number in the denominator. And the reason why we don't want to have an irrational in the denominator is because when we're actually doing calculations, it's much easier to have an irrational number in the numerator than it is to have one in the denominator. So for calculation purposes, it's much better. But then the reason why we're so obsessed with it is that we want to just have one specific value, one specific expression that represents all of these different values that have the same value. So that's why we rationalize denominators. And it took me a really long time to figure that out. So if it seems kind of abstract, well, that's because it is a little bit abstract. But hopefully that gives you a little bit of an idea as to why we do what we do. Okay? So let's try a few more examples where we're rationalizing a denominator. Okay? If I can ever just get undistracted from Goose right now. Oh, she's just being so precious. Oh, and now she wants to eat my pencil. Okay, let's get back to work here. No more horsing around. Okie dokie. Okay, let me find a good question. We'll do that together. Okay, let's try. Okay, Oh my goodness. Oh my goodness, Goose. You're getting kind of crazy. Can you blame me? Can you really blame me when you have this? Okay. Sounds like I'm not alone. Okay. Okay, so where were we? Okay, so let's simplify. Oh, and by the way, like you know how in a test it's sort of assumed that any fraction is going to be reduced. Like when you write your final answer, it's expected that your solution has reduced fractions. It's the same thing with radicals now. So anytime you write a solution, I expect that the radical that there is no radical in the denominator. So all radicals should be in the numerator, and all that you have in the denominator is a radical. Now, just to give you a heads up, like, because I think that a lot of us are in the long game here for mathematics, right? We're not just here just to sort of, do our time and kind of move on. I think a lot of you guys are thinking about the future and how, maybe when you're older, you want to go to university and study calculus and that kind of thing. I just want you to know, sometimes it is useful to have a radical in the denominator. And that's just for calculation purposes. So just like how sometimes you might have to blow a fraction up and have it not reduced, like for example, when you add fractions and you have to find a common denominator, you might have to convert those fractions into fractions that that are not reduced, right? Like for example, like if I have one half plus 1/3. If I add those together, I have to do this, right? And I have to do this, and then I'll get 3/6 plus 2/6, right? All of a sudden now those aren't reduced anymore, right? And I did that on purpose. Just like that, you may come across sometimes, especially in calculus, when you actually have a radical in the denominator, and you do that on purpose. So it's not like having a radical in the denominator is bad. Like I don't want you to think that it's bad. It's just that it's kind of like a reduced fraction, right? It's like it's the clean version. It's the representative expression to represent that value. So you may, like in your travels, in your mathematical travels, you may come across some expressions that have a radical in the denominator, and that's fine. Just know that like as a final answer, when you're just writing a radical all on its own, then that's when you want to get the radical out of the denominator. Anyway, so let's simplify. Let's simplify the cube root of 2 over y. And here we're saying that y is non-zero. Okay, so we get the cube root of 2 over y. So I'm gonna write it over here. I've got the cube root of 2 over y, and that's equal to the cube root of 2 over the cube root of y. Okay, so that's fine. So what we're gonna do then is multiply the numerator and the denominator by the cube root of y. Oh, sorry. We're not going to multiply by the cube root of y. We're going to multiply by... Okay, Goose, she's grabbing the tip of my pen. I don't know if you can see that, but it's making it very hard to do my work. We are going to multiply it by the cube root of y squared. And you might wonder why we're doing that. Cube root of y squared. Why would we multiply by the cube root of y squared? Well, just take a look at what happens in the denominator here. In the denominator, what we're going to get is, well, first of all, I'm just going to write the numerator. So I'll say that the numerator is cube root of 2 times the cube root of y squared. Now in the denominator, we're going to get the cube root of y times the cube root of y squared. And when we simplify that, I guess I didn't really change anything there. Let me write it one more time. So I'll say that the numerator is equal to the cube root of 2 times y squared, which is fine. And the denominator is equal to the cube root of y times y squared. Okay. Now you can probably see what's happening here. So I've got the cube root of 2y squared in the numerator, and the denominator is the cube root of y cubed. Isn't that nice? Cube root of y cubed, that's just y. So the final answer is the cube root of 2y squared all over y. Which is nice because now our denominator does not have a radical in it. It just has a variable. Okay? All right. Let's see what's happening next. Okay, Goose, you're being just a little monster right now. You'd think that she's hungry or something. I just fed her. Okay, let's do... Yeah... I'm just trying to think of which example I want to do next. Yeah, let's do this example. Okay. Start a new page. Okay, Goosey, you're just being a little too much. I gotta put you on my lap. There we go. Okay. Okay, next question. Let's simplify. Let's simplify the fourth root of 5x over the fourth root of 10x cubed. 10x cubed. Okay? So those are the ones I'm going to simplify this. So I'm going to simplify this. So what I need to do is I need to do a couple of things. First of all, I'll be able to simplify this radical without even rationalizing the denominator. You might notice that 5x and 10x cubed have some common factors, so we're going to get rid of those. I should also point out, in this case, x is non-zero. So that's important, because if x was 0, then we'd have a problem. We'd have 0 over 0, right? So it's important to point these things out. So in this case, x is non-zero. X, in this case, you could think of as a non-permissible value. Okay, so the first thing I'm going to do is I'm going to write it as one big radical. So this whole thing is the fourth root of 5x over 10x cubed. Okay, and we can do that because that's how radicals work, right? If I have a fraction of radicals, that's like a radical of a big fraction. So now that I've got it written like this, I can simplify it. So that's nice. Take the fourth root. Well, the 5 and the 10, they've got a 5 in common. So these cancel out. I'm left with a 2 left over. And this x and this x cubed cancel out. So I'm left with x squared on the numerator. So then denominator. The numerator in this case is now just 1. And here I've got 2x squared on the bottom, which is nice. Okay. Now I'm going to convert it back into a fraction of radicals. So in other words, I've got, well, the fourth root of 1 is just 1. And the denominator, I've got now the fourth root of 2x squared. Okay. So now what my job is, now what I have to do is multiply the numerator and the denominator by something that's going to get rid of the fourth root on the denominator. So let's think about how I could, so it's going to have to be a fourth root of something. Let's think about how I could get rid of that 2. Well, 2 is not a fourth root, right? I can't take the fourth root of 2. If I multiplied it by 2 again, I would get 4. 4 isn't a perfect fourth power. If I multiplied it by 2 one more time, so I would get 8. That still wouldn't quite get me there because 8 isn't a perfect fourth power. So if I multiplied it by 2 one more time, in other words, if I multiplied it by 8, I would get 16. and 16 is a perfect fourth power. So let's multiply it by 8. So in other words, I'm going to multiply it by 2 to the power of 3. And another way you might want to think about it is that this is 2 to the power of 1, right? I want this to be something to the power of 4, so that when I take the fourth root of it, that they kind of cancel each other out, right? So 1 plus 3 is 4. That's another way you can think about it. So that's how I would get rid of the 2. Let's think about how I would get rid of the x squared. Well, if I multiplied it by x, I would just get x cubed. And I can't take the fourth root of x cubed. But I could take the fourth root of x to the power of 4. And I could get x to the power of 4 if I multiplied this by x squared. So I'm going to multiply the numerator and the denominator by this. So I'll take the fourth root of 2 cubed x squared. That looks good. And what I'm left with is the following. I've got the fourth root of, let's simplify that a little bit. The fourth root of, 2 cubed is 8. And I've got x squared. So I'm going to take 8x squared on the numerator. And the denominator, I'm going to have the fourth root of, 2 times 8 is 16. And x squared times x squared is x to the 4. And I can simplify this. I've got, I can't do anything to the numerator anymore. This is the fourth root of 8x squared. And the denominator is, the fourth root of 16 is 2. And the fourth root of x to the 4 is just x. And just like that, I've rationalized the denominator. So that's that. Okay. Now for kind of the next level of rationalizing denominators. This is kind of where things get a little more challenging. So here we're going to be talking about something called conjugates. Okay, so we're going to talk about conjugates. Okay. Okay, so the conjugate of a plus b is a minus b. Okay, so if I have an expression that's like a sum, then the conjugate of that expression is where I would change one of those signs to be minus. So so this is going to be really useful when we rationalize a denominator because of this. So notice that a plus b multiplied by its conjugate, a minus b, you might know that this is this is going to be a difference of perfect squares. Okay, this will be a difference of squares. So take a look at this. So a times a is a squared. Here we would have a times negative b and then b times positive a. So those would cancel out. And then we're left with b times negative b, which is negative b squared. So that's pretty nice. And so we can use that to our advantage because we can rationalize denominators by multiplying things by its conjugate. And another thing, just sort of about the future and some things that you might see later on in your mathematical career, there's different kinds of conjugates. In particular, there's something called a complex conjugate, and that involves complex numbers. And there's many different kinds of conjugates out there. This is the first type of conjugate. And conjugates are very useful in algebra. It's kind of like a tool that you can use to change a value. So let's use a conjugate. So I'm going to say use the conjugate, I should say. Use the conjugate to simplify. And what I'm going to ask you to simplify is this guy right here, 3 over 2 minus the square root of 5. So look at that. We have an irrational denominator. So that's a problem here. So like if you just tried to attack this by multiplying the numerator and the denominator by root 5, well, you'll notice that you'd have to actually distribute that root 5 throughout, and you'd get rid of the irrational number here, but then you would introduce it here, right? So if you just multiply the numerator and the denominator by root 5, you'd have 3 root 5 in the numerator, which is fine. We don't really care what's going on in the numerator. But the denominator, not so nice, because we would have 2 root 5 minus 5, which now you've just moved the irrational or the radical somewhere else. So that's not going to be very helpful to us. So let's rewind a little bit. And what we're going to do is we're going to multiply the numerator and the denominator by the conjugate of this to simplify it. And you'll see what happens in a second. So what we're going to do is we're going to multiply by 2 plus root 5 over 2 plus root 5. Okay? So I took the conjugate. I just changed that middle sign, and that should take care of business. So let's try that. So this is equal to, well, I'll have 6 plus 3 root 5, right? You have to remember that we're using the distributive property here. And I'll use the distributive property one more time. So here I've got 2 times 2, which is, oops, that's not what I meant to do. I've got 2 times 2, which is 4, right? 2 times 2 is 4. Then I've got 2 times root 5, and then negative root 5 times 2. So those would cancel each other out. And I've got negative 5 times positive root 5, which is going to be, well, root 5 squared, which is just 5. Okay? You know what? You know what I'm going to do, actually, just to be absolutely clear about what we're doing, because this is the first time we're doing it. I'm going to write the whole thing out, and then you'll see exactly what's going on. I feel like I might be skipping too many steps. So let me redo that, and I'm going to just write everything out. So I've got 2 times 2, which is 4. In fact, I'll even write it as 2 times 2. So this is 2 times 2. And then next I've got 2 times root 5, so plus 2 root 5. And then here I've got negative 5 times negative root 5 times 2, which is minus 2 root 5. And then finally I've got negative root 5 times root 5, so that's going to be minus, well, root 5 times root 5, we'll see, is just going to be 5. So that's what we get on the denominator. And I'll just sort of move this and center it so it looks nice. And then finally, when we clean this up, I'm going to have 6 plus 3 root, let me write that nicely, 6 plus 3 root 5 over, well, 2 times 2 is 4, 2 root 5 minus 2 root 5, they cancel each other out. That's kind of the whole point of using the conjugate. That's the trick. That's why we do it, is because those middle terms cancel each other out. And then finally we have root 5 times root 5, which is 5. So I'm going to have minus 5. And then this is equal to 6 plus 3 root 5 all over negative 1. And the nice thing about negative 1 is that it's pretty much just 1, except negative. So this whole thing is just equal to negative 6 minus 3 root 5, because I divided the whole thing by negative 1, which is the same thing as multiplying the whole thing by negative 1. So there you go. So there's something that had, not only did we start off with a irrational denominator, but we ended with something that had no denominator. So it's much more straightforward. So that I'm hoping is some motivation for you as to why we do what we do. So I'm running out of time here, so it's 11 o'clock. So what I'm going to do is I'm going to post the homework. And like I say, it's gonna look like super long. Like it's gonna be like 10 pages long. I don't want you to do 10 pages of homework. That's not my intention. I'm just gonna pick and choose, just cherry pick some questions. It'll just be easier for me if I just give you the whole thing rather than me having to create a whole document. I just don't have time for that right now. So I'm gonna post the homework in about an hour, and you can get started on that. It's not worth any marks. It's just for your own practice. And if you have any questions about it, let me know and I can address those in the next live stream. So just know that We have Good Friday tomorrow, which means that we will not be having any classes, so you get a day off tomorrow. At some point, what I'd like to do is I'd like to take a survey, and I'd like to put it on the website, and I just want to get a little bit of feedback from you about how things are going, if there's anything that I can do to make this more enjoyable for you, or maybe if like maybe I'm assigning too much homework, maybe I'm not assigning enough, maybe you want more things that are worth marks. I don't know. It'd be nice to get some feedback. So I think next week I'll put a little survey on my website that you can take just to give me some feedback, because I've never done this before, as you can imagine, and I don't think any of you have done this before either. So I think that this is a great opportunity for me to learn and get some feedback from you, because I really want to know sort of what's going through your mind. Like, is this working? Is this not working? Like, what can I do to make this better for you? Because who knows, maybe you have some great ideas that could make it better for everybody. So so next week I'll put a little survey on my website. Anyway, I'm gonna log out now, and I will talk to you guys on Monday of next week. So have a good long weekend. I hope that you can manage to have some kind of fun time. I know that this is typically a time that families get together for Easter. And it's going to be a little bit different this year, but we're just going to do our best. So yeah, I hope that you have a good weekend, and I'll see you guys on Monday. Bye-bye.